Okay, so we're going to be delivering new content that is separate from the live call, that is higher resolution and provides more information about what we're doing and what will be provided to the members. So I'm going to show you what we've done with the toroidal winding so far um, and go over the parts of the toroidal winder so it is more clear about what they do, so that when you get the parts, when you get the file and you download the file, you know what each part is. So I'm going to share my screen now and we'll go over the parts on the CAD program that I'm using. Okay, so with this toroidal winder, it's mainly made from sheet metal. And that has been the most convenient way of making this winding machine that you see here. Also the most cost effective. Most parts of the world has access to sheet metal. So if you have someone that can laser cut, hopefully stainless steel, but you can also do this with mild steel, and you have a supply of nuts and bolts, mainly for our use for this build was M5 and M6 bolts, nuts and bolts and spacers, then you're pretty much more than halfway there with constructing your own large format toroidal winding machine. So this winding machine is made from really three main components, plus the supports to keep it mounted to whatever surface or table and wall and structure that you need. But mainly we're looking at the actual frame itself, looking at other projects and other builds of toroidal winders. If you go through a search online, you find that they can be made out of cross T-junctions or beams. In this case, we actually went with a round C-shaped format for our structural frame, which again is sheet metal. It's 3 millimeters thick. And you have the actual winding form, or what would be your bobbin, the actual metal ring itself that you would wind your wire around. Now you've seen if some of you have been doing research on toroidal winders for a while, you'll find that there are some DIY instructions that show how you can actually take the bobbin itself and basically fit it within a round form. But that kind of defeats the purpose of a toroidal winding machine, and I say that because the purpose of having a large rim like this in a toroidal winding machine is that this rim is actually the bobbin. So you'd have to take the time to find a way to wind this rim full of the enamel copper wire, especially if you're winding something that requires thousands of turns around this rim, which means you have to take some consideration into how you're going to spin this rim, the transmission used, how you're going to take the sector off this rim needed to fit it around the iron toroid or donut, your stator or copper transformer, your iron transformer core, and put the sector back on. And I'm referring to this section here. This has to be detachable so you can actually slide the bobbin, your stator, inside this frame and then reattach this sector. So that has to be taken into consideration. And then on top of that, you need a way of carrying the wire from the bobbin onto the second rim, which is approximately the same diameter, this thin rim here. And it's this thin rim that's actually going to be carrying the wire or guiding the wire onto the stator. So in this build, we've decided to take this carrying rim and turn it also into part of the transmission to move the wire around the stator by adding these this just giant these gear sections onto the rim itself. Now there are 8 sections that will be welded together to create this rim. And like the giant bobbin that you see right next to it, it has to have a sector that can be detached. And for our purpose, it's this sector, and it coincides with this sector of the bobbin itself, so that you wind you can wrap both of these rims on the inside of the stator, or the inside of your transformer core, and then reattach them. And you reattach these things with the use of these metal clamps or little shims on these. So these are specially designed pieces, again, out of sheet metal, that will allow you to reattach the sectors. So then once you do that, then you can wind large size stators for larger generators and larger transformers. And this is probably the first time where there's been an open source project with plans to be able to make your own winding machine, saving you, upwards of 10 times the cost of even trying to get one built and have it imported to where you live. I've done the cost analysis of how much it would cost to have something like this, a large format, large diameter winding machine made and then sent to you, unless you live in Asia or India, and you're looking at 6 figures, or at least correction, you're looking at 5 figures for that, anywhere from $60,000 to $100,000 easy, because this isn't a standard size format for a winding machine. So you have to build it, and these are important because if you're looking at multi-kilowatt generators or alternators you want to build for DIY off-grid projects, if you're looking at large format transformers to carry the amount of electricity needed to power either a village or a large home, then you have to look at having contraptions built that will allow you to do that, to facilitate that. If not for you, for your business, so that you can provide a service for the customers in your community that need that. So that's why this project is important. Okay, so we've gone over 3 sections of the winding machine. The 3 most important ones are the actual structural frame, the actual bobbin itself, and the actually carrying transmission, what I call the rail guide, that carries the wire from the bobbin onto the actual stator or transformer core. And the design of this rail guide is what makes this particular embodiment of the toroidal winder very important, because again, it's able to do that because it's being driven by transmission teeth of gear wheels on the periphery of this toroidal winder, and the transmission, that energy is being transmitted through these gears onto this larger, the teeth of this larger geared rail guide. This is made possible with the use of a stepper motor that's not on this CAD program, but if you look in the lower right corner here, you see at the base, you see a section where you have 4 mount holes and a larger hole in the lower right. And that's where a stepper motor will fit right on the inside. Actually, I think I can show you that right now. If I just change the screen back, actually you can see me in the lower right, but I'll go back to the camera here. And this is the stepper motor, and I got the shaft coupler that has the appropriate diameter on the end to take another shaft attachment and project it through the actual toroidal winder on the other side to connect to the rest of the transmission. This stepper motor is a NEMA 34. It's on the higher end as far as power and torque. It might be overdoing it, but we have a large frame here, and when you add all the copper, thousands of turns of copper that we intend to have on this winding machine, I wanted to make sure that the torque was there to move these rims all the way around that stator. Now, this is going to be a stepper belt driven transmission. So that stepper motor is going to be driving this 4-to-1 stepper belt drive, and you normally see these in robotics. And so it's going to take the high RPM of the stepper motor and transmit it into this larger gear, providing the torque needed to bring that large rim around. So that's going to be the drive, and I'll go more into that. So back to the CAD program. Right, so what you see are 4 wheels. Now, the wheel in the lower right is the main transmission wheel. It is where all the energy is going to drive the rims. The other 3 are simply coasters. They're there to make sure that the 2 rims stay in place, the bobbin and the rail guide, and to help evenly transmit the transmission, the energy, all the way around and keep everything in place. And when you look at how these 2 rims are mounted, the bobbin that would carry the copper is on a rubber or nylon wheel, and it's driven in one direction. Let's say if you want to charge the bobbin by itself, it's on its own independent transmission with a one-way bearing at the bottom here. It's actually connected to a one-way bearing, which means it will collect wire when you put the machine in winding mode, and it won't affect the transmission of the rail guide. But then when you're ready to actually wind the wire onto the actual stator or transformer core, then the other transmission, again, which is a one-way bearing based transmission going the other way, would only drive the rail guide and would not affect the actual bobbin itself. And the bobbin would simply be pulled along with the rail guide as the wire is being unwound from the actual bobbin and being pulled along with the rail guide around the actual around the stator. If you look at some videos on how toroidal winders operate, you'll be able to get your head around it. But basically, when you see them in operation, and when this carrying rail guide moves the wire around the stator, it's literally just pulling the bobbin along, and the bobbin is sliding along its wheels. So you need to have a decent amount of friction between the stainless steel rim that I'm using as the material for my wire bobbin and the actual rubber or nylon wheels. So I'm still deciding on what material to use for these wheels. By the way, they're colored in orange here. But I'm looking at anything from a yellow or like an epoxy or plastic or thermoplastic, or even like a rubber consistency wheel. I'll have to have these machined to fit the bearings I bought for this. Yeah, but so you have basically 3 coasters. And then you have at the lower right, you have the main transmission that I was just telling you about that's going to be connected to the stepper motor. So if I was to move to this side, what you'll see on the lower left there is the output shaft coming from the stepper motor. And it'll be connected to the gearing system that I mentioned, that I showed you before. And you see the second shaft that goes through a bearing. And that's going to be the main drive. And if I can zoom in here, you'll see that it is connected to a gear mechanism, and that's what's driving this giant rail guide to wind your wire. Now this shaft that is connected to both the rail guide and the wire bobbin. And again, that bobbin is connected through the rubber or plastic wheel. And when any of the drives are engaged, the other one basically coasts in that direction with no problem, with little effort. So, but in any given moment, only one of the drives is engaged, and this is made possible because as the shaft either moves forward or in reverse, one of the one-way bearings is engaged in one of the directions. So that's how you're able to drive something in two directions and only really engage one of the mechanisms, and the other one is either being pulled along or coasted along through the wire. Okay, so this is the kind of thing you'd have to deal with that problem of wanting to go forward and then reverse. You'd have to have one-way bearings. At least our solution is the one-way bearing system. Okay, I think what we'll look at now is the base, or it is supported on a platform through these brackets. And what we have here are two main brackets. We have a rear bracket, which you look at is generally two plates that are attached to the frame, to the support frame. So it's basically these two plates that are highlighted there. And then it is these plates are also attached to basically like a T-frame of what would be welded steel, stainless steel or carbon steel, but I'm going with stainless steel for this project. And this makes up a base, a rear bracket support plate that can be both clamped and bolted to whatever structure you would like to attach the winding machine on for further support. Could be a table or a table against a wall, whatever your situation is in your garage and workshop. Okay, the second mounting brackets are the front mounting brackets, and they are these. And there are a lot of options. When you look at, there's all kinds of holes, mounting holes and support holes on this bracket. So the large and middle size diameter holes are for bolting to the surface to give added support, especially for the front for such a large metal structure. What you also have are M4 holes. You can see 3 pairs of M4 holes here. And these are for if you wanted to attach some kind of sensors or encoder equipment, Hall effect equipment, for however you want to modify your electronics in the future, you can. So we made those available. And now obviously this means that you'd have to put it through the actual structure of the surface. So for our build, what we're probably going to do is have this primarily mounted on like a wooden flat surface, maybe an MDF or a combination of MDF and steel, and have some holes drilled underneath this structure in certain areas, so that if we want to attach sensors and things in the future, we can. But the point is, there's holes in this bracket for that kind of modification. What you also see here in this bracket is we've added this slot. It's a chamfered slot here. See if I can highlight that only. You can see it here. If you zoom in closely, it's actually chamfered. And we plan on having our wire that we wish to wind underneath the table and feed it through a hole through the table. So it comes through where basically these wire guides here, there's like a V-cut opening based on the design of these bearings, and they act as wire guides. We're going to bring the wire up through the table, through this slot, through these wire guides, and the idea is to have it from there wind around the large bobbin. Have it wound around this. Let's see if we can get a side profile here. So this is a side view, and on that side view you'll have the wire coming up from under the table through the middle of the bearings and up around the large bobbin. And that's how we're going to approach it and see how that goes. But it gives us some options on how we wish to move the wire onto the bobbin. Now, since we're talking about the wire, let me see if I can show you. I'd like to also show you how this looks with the bobbin removed. when it comes time to wind the wire from the bobbin onto this rail guide, you know, you're going to have to feed the wire from the bobbin onto the rail guide. What we provided are the parts for these, what we're using. I'll go back to my large video camera, are these special bearings here. So we get the focus. That might be a bit far. Okay. So we have these special bearings, and what's special about them is they have a V-cut groove on the side there. There we go. And this gives us, we thought about using this for as a means of you can put wire, is big enough to fit wire right in between that. There you go. And also you can use these to, you can basically attach this to a rim and feed wire around the rim of the guide wire. So that's what you're going to see in the file. Is if we zoom in, we go to the 3D view here. You have the V groove bearings here, and we're using that as tensioners around the actual rail guide. So imagine the bobbin that we just removed. Wire is coming from that bobbin. It's going to feed through this wire. This is wire guide here. Let me just highlight the other two. Got the wire guide there. The wire will feed through that. And then if you wanted to add more tension to the wire before it goes around the stator or transformer core, then you can feed it, let's say, under this bearing and then above this bearing. Or if you wanted to use both pairs of bearings, you have 4 additional pair of bearings to wind the wire around for added tension. So basically, these 4 bearings you can use before actually winding it around your stator. So that's basically the complete rail guide rim there. And that's probably one of the most important part of the actual device. But we have that's basically what's there. And these are all the parts to make that. That will be in the file provided. So the step file is pretty much complete. There's only a few more holes needed to complete for this front bracket. But all the parts have been made, have been for the most part designed. If you look at the rear bracket, again you have M10 holes that are spaced to give you solid support. So this should be a fairly rigid contraption once everything is bolted down. If we want to go into some specifics, some key features is that with the coasting transmission, these 3 coasting wheels I was telling you about, they're all supported by M12 bolts that are basically being bolted all the way through the housing here. There we go. This is one of the M12 bolts. And this M12 bolt, what's also in the file is 3 round nuts. And these 3 round nuts they actually thread onto the bolt, but they also act as spacers to attach your bearings for the 2 different transmissions. So those are the 3 round nuts, and you have, now these bearings are generic bearings. They're not special. They're not one-way bearings. They're just normal bearings. You have a bearing there, and you have another bearing there, and you have either they're the same bearings, but either have a attached. They're going to have to be press fit into either a gear or press fit into one of these plastic nylon or rubber wheels. And so that's, you have 3 sets of those. And again, the parts needed for the actual transmission on the back here is the customized set of bearings that are unique, as are the gear. It's also unique. It's not like the other 3. And the dimensions of the plastic wheel for this is slightly different also. Its inner diameter is different as well. So that has its own set of customized parts. But what you'll have are you'll have packages or folders in the total package that will be available for the members, where everything has, all the parts are named by alphabet. So all the transmission for, like the transmission shaft that's connected to the stepper motor, that has its own set of customized parts that are together to try to make everything make sense when you want to make your own. Also, you can just go ahead and you can design your own design based on what you have for the frame. If you have the frame and you have the main stainless steel structures, you might decide to design your own shaft and gearing mechanism. But at least by having these CAD files, you can actually either 3D print or CNC these to spec, and you know that they would fit because I've already done the legwork for you. With regard to the actual CAD file, so I'm really excited about it because I've started to construct this project, and so I'm waiting for more parts to come in. So I'm looking forward to having anyone else, if they wanted to build a toroidal winder for their own project, we can share notes and talk about what they're doing if they have any questions. But these files will be available very soon. The step files are pretty much already done, but what I'm working at now is making other file formats and schematics for some of these parts as references and guides, so that when you go to get them made, if you have a CNC or machinist shop ask you, do you have a PDF or a schematic, so that for reference, that would be available too, so that they can actually look at numbers along with the part that they're either 3D printing or doing CNC work on. So I'm looking at getting more, so that's what I'm doing right now, is generating more files in different formats, PDF, DXF, or maybe .3DM, in addition to the step format that most companies use today. So that is the end of this video, and it will probably be part of a compilation of other things that will be in the larger addendum. So that's all I have for now. Looks like all the pieces are here. This is going to be connected to the giant cog or rail guide, or follower they call it. This is going to be the bobbin, the wide rim here. The sections have been laser cut, and the thin pieces for the actual rail guide has also been laser cut. And we got this is the clamps for the big section as well. And these are little ones for the thin wheel, for the thin rim, for the follower also. And we even have to swivel up and down to put these rings on this going to be giant toroid winder. So I'm really pleased with it, and we'll have a proper look when we get back to the house. This is just in the trunk of the car, and it begins.
Okay, so that's the area that we're looking at. These two parts made. We got the actual bobbin that's going to be winding the copper wire, and we got this cogged rail uh, wire guide that's also a ring or a rim, but it's toothed and it's going to be part of a transmission to feed the wire around the stator. So we got those laser cut along with the actual frame, and this is what we've assembled so far. So this is basically stainless steel sheet metal. This is 3 millimeters thick, and the actual rings themselves are 2 millimeters thick. And they've basically been assembled by lots of nuts and bolts and spacers in between of the right width. As you can see there, and as you can see here. And this was basically based on cost and price of having that much material, like the least amount of material, but structurally sound to make a large frame. And as you can see in the CAD drawing, what we're also going to have are brackets to support this large frame. And those brackets have other bolts that allow for more fittings, like if you want to have other encoders and optical sensors and things like that. That rear bracket that will also allow you to mount to the back plate of a table or a wall for further support. Also has a metal beam coming out from the back as well for added support. So the idea is with these plans you can have basic machining and assembly done with cost as a consideration. It's obviously cheaper to do things with sheet metal than solid pieces of metal that would have to be CNC machined and fashioned. So I like how this project is moving forward so far. Again, this is the giant bobbin that you're going to wind your wire onto. So the wire is actually going to be wound onto this giant ring, and that's called charging the toroidal winder. And then it's going to go in the opposite direction. With this ring, I'm waiting to get the actual teeth or gearing teeth to go around the rim. I'm waiting for that part to come in. I'll have to weld it all in place when it comes here. It's going to come in pieces. But when we unwind it onto the stator, it's going to go in the opposite direction, and this will wrap it around the stator. Now what's great about this also is when you get the sheet metal, it might be misaligned, but just by bending it with your hands and manipulating it, you can get it to straighten out. And when you put it in with the fasteners, it ends up falling pretty much flat and straight on. The tolerances are great, and I don't think we're going to have any problem doing this large assembly. If you compare the prices of trying to buy a toroidal winder, most of these things are made in Asia or in India, and what you would get for something maybe like instead of a rim this large, you get something maybe half the size with all the automation. You're looking at that actual machine to cost, depending on how automated it is, between $8,000 to $12,000, $13,000. That's not including transport costs and customs fees. So just double that. You're looking at about a $20,000 to $30,000 machine. And that's for something that gives you a limited stator size to wind around, because the winding, the bobbin and the actual winding mechanism is only half the diameter. Now, when I try to look for large toroidal winding machines online, just Google images and go on Alibaba and sites like that to find what kind of prices you'll see for something anywhere near this size. Look at doubling that. Anywhere between $50,000 to $100,000. So the savings are enormous by having the plans yourself getting the stuff done by fairly simple machining means, and you assembling it yourself, you can do it. We're hoping the budget will be within between $2,000 to $5,000. Might be even $2,000 might be a high point. I will price all of this at the end when I'm fully assembled it and have taken all the parts I used and come to a fair assessment. But needless to say, you're looking at maybe a 10x gain in savings if you assemble this yourself. So this is why we find this project is very important, especially for anyone who are part of a small community or a small company or business for their local town or village to be able to provide a service where they need to wind large stator windings for off-grid generators or transformers of special designs, special winding types. This is the way to do it. A DIY, build it yourself, open source toroidal winding project. So this is what we have so far, and parts are still coming in to continue assembling. And as they come in, I will give you another update.